Okay, we have this system of two equations. Following procedures that I've used previously, I number the equations so I can document what I'm doing to the equations. Now, I could eliminate y if I multiply the first equation by 2 and the second by 3. So multiply -6 by 2, I get -12. And multiply 4 by 3, I get 12, right? So I'd have a -12y and 12y. Or I could multiply this equation by 5 and this one by -4. Okay. I could do it either way. And just to illustrate it, I'm going to go ahead and eliminate x first. Now, if I was doing this, trying to do it quickly, I'd probably multiply this one by 2 and this by -3. But I'll do 5 times 1 and -4 times equation 2. Well, I'm going to write out this step, although I really don't want to take the time. It's to emphasize on both sides. Now equation 1 becomes 20x times 30y equals 180. And equation 2 becomes -20x minus 16y equals -80. And now I add 20x and -20x gives me 0. 30y, -30y, and -16y gives me -46y. And 180 and -80 gives me 100. So y equals -100 over 46, which is -50 over 23, which I saw on a number of papers. Okay. So pretty straightforward. And now what do? We take this result, we plug it into one of the equations, could be the second one, but it's easy for me to get an arrow to this y. And that gives me the equation 4x minus 6 times -50 over 23 equals 36. Now, how do I solve this equation? I don't want to deal with the denominator. Multiply both sides of the equation by 23. I'm actually going to take a step. I'm going to multiply the -6 by the -50. Making a little change there. It's equal to 23 times 36. You understand that I multiplied the -6 over 1 by -50 over 23, and I got 300 over 23. Now I multiply by 23. 23 times 4 is 92. 23 times 300 over 23 is 300. And oh boy, 23 times 36. Well, that's 1,080 plus 3 times 36, which is 108. So it's 1,080 and 108. So it's 1,088. I hope. Okay. And if it's not, well, some kind of close. Yeah. Okay. So this gives me 92x equals 788. So x equals 788 over 92. But 23 should go into 788. I don't know that it does, but. And it should be, well, 20 times 20, no, 30 times 23. No, 40 times 23, 30 times 20. Okay, 30 times 23, 690. And then that leaves 98. 13 goes into 108. That's good, 98. Something wrong with my arithmetic here. 6. That's 720. Oh, wait a minute. 3 times 36 is 108. $528. And 23 goes into 528. Okay, I'm not gonna take the time to get too hung up on the numbers here. If I divide this by 2, I get 264.6, which is 132 over 23. And that is the number that I saw, so I actually did the arithmetic right after a couple of stumbles. Okay. And then to check this, make sure it's right, plug these numbers back into the second equation. Because plugging them into the first equation just tells me that I solved this equation correctly. That this equation, tells me, never mind. If this solution, these two numbers come just from the first equation. Okay. If I made a mistake getting this number and then solve this equation correctly, I wouldn't have a solution to the system. So I've got to check the second equation. And that would be 5x plus 4y equals 20, which comes out to 5 times negative 50. No, that's 5 times 132 over 23 plus 4 times negative 50 over 23 equals 20. And multiply everything by 20 by 23. And I get 5 times 132 minus 4 times 50 equals 23 times 20. That's 460. This is 660. And that's 200. And 660 minus 200 is 460. I did that kind of fast. Because if I stop and think, I'm going to screw something up. Okay. Fortunately, it seems to have checked. Now, what did I do between this step and this step? I had denominators. I don't know what it takes to convince people that if you got denominators, you get rid of them. Okay. This equation with all the fractions, multiplying by 23, multiplying every term by 23 eliminates the fractions. Gives you kind of big numbers, but it's much easier to deal with those big numbers than it is to deal with the fractions, especially if you got a calculator to do your multiplications and additions, okay? And down here, this becomes a lot easier if I multiply everything by 23. The 23s will go away. I'll still have 23 times 20, and it all works out very quickly, okay? This is especially important when you're solving equations. You could work these fractions out, find out that the fractions are equal. That would be a valid check. One thing we don't do is we don't do decimal solutions. Okay. Now it's fine when you get down to here, you say, okay, that's about negative 2.2. Okay, this is once two significant figures, it's about negative 2.2. And this is about negative 5.7 or something like that. Okay. It's okay to do that approximation, especially if you're going to try to locate those numbers on an approximate graph. Last thing I'll say is we can graph these two equations. I chose them so they'd have nice intercepts. X-intercept is 9, 0. Y-intercept here is negative 0, negative 6. There is my equation, 4x minus 6y equals 36. Now expect on a test, I'm going to ask you to do all this. Okay. Second one, the x-intercept is 4, 9, 0, 4 is here. Sort of. It'll be a little more to the right. And if x is 0, y is 5. So let's see, if that's negative 6, then y is 5 ought to be about here. There are my two intercepts. Here's my straight line, and here's where they cross. I can estimate the x and y coordinates. If this is negative 6, that looks like about negative 2. This is x equals 4, and this is x equals 9. Then this is y, it's about, it's like 5.3 to me. Now, if you compare that with the decimal equivalents, you'll find that this is probably a little bit off. It's 5 times 23 is 115, and 0.3 is going to give you another 7. It's going to come up a little short. But it's plausible that these numbers are close enough to these numbers that you now believe pretty much everything you did. Okay? And mathematics is largely about being able to believe everything you did and know what it's telling you. So that's system of two equations and two unknowns. Expect to be able to do all of that very well, because next week we're going to be moving into 3 equations with 3 unknowns. Okay. And on the whole, I mean, you know, what I saw, most of you did quite well on this. Okay. If you didn't, review the steps. Okay. Okay, well, I just asked everybody to sketch the graphs of the toolkit exponential and toolkit logarithmic functions. So exponential function. And I'm doing this without any, no, we don't need that. Doing this without any explanation, because everybody is pretty good at this. And if you aren't, you need to review. There we go. Okay. Now, for the toolkit function, Graph goes in a 4x4 box with a red dot at the origin. And there are labels, and we can get the coordinates of the point if we need points if we need to. So we can easily make a table of these points. Of course, they can be calculated easily also. We'd easily make a table of these points and then reverse the columns, and we would get a graph representing the two log function. Now, if we reverse the coordinates, they all still fit into a 4x4 box. But turns out that your points look like this. And the graph looks like this. Now, we've done it just by plotting points, do this, make the table, do the table, make the table, reverse the table, and then plot that, okay? If you do it by construction, it looks like this because x's become y's and y's become x's. So we divide the vertical lines we use are like the horizontal lines we used here. Okay? And the horizontal lines are like the vertical lines. The other thing that though is that still a 4x4 rectangle, but here now y equals -2 here and y equals 2 here. X equals 0 here. X equals 4 here. That makes a certain amount of sense out of this graph because here's the point 0, 1, right? X is 0, y is 1. So this point is going to correspond to this point where x is 1 and y is 0. So our x and y axes, this function, here's the x-axis. Here's the y-axis. This picture, where's the x-axis? It's at y equals 0, it's in the middle. It's the y-axis, it's at x equals 0. So if you try to put these two graphs on a set of coordinate axes, rectangle, here, this line is x equals 2, negative. This line is x equals 2. This line is y equals 4. And of course, y equals 0 is your x-axis. This one is going to be situated a little differently. Your x-axis, which is your y equals 0 line, is here, so that this rectangle is cut in half by the x-axis. And this line is x equals 4. This line is y equals -2. And this line is y equals 2. So the graphs look pretty much like this without doing all the subdivisions. Let me outline the 4x4 rectangle for the log function. It goes here. I'll go ahead and okay. These graphs don't necessarily go where you expect them to, but now if you draw this graph and label it correctly, you can make estimates of the log. Okay. If you make the table and then reverse the coordinates, it's going to look like this. And you know that from your book. You know that from the homework you've been doing. Okay. Now what I want to do is I want to say, okay, now where's the graph of two times log two of x? What would you do to construct a graph of two log two of x? Well, you would take the points of this graph. I'm going to mark a bunch of points that don't necessarily correspond to the construction point. Multiplying by two, let me label these graphs. X here. This is your 2 to the x graph. If I want 2 log base 2 of x, I have to multiply all my y coordinates by 2. Now, what's the y coordinate of, let's say, this point right here? Well, I could draw a little dotted line there. There's the y coordinate, right? What do I get if I double the y coordinate? Well, it has to go twice as far from the x-axis, right? Because you know, here we're cutting y coordinates in half. Want to double them? Well, we just do the opposite of what we're used to doing. So this value would go up maybe to here, this being about double this. So this point would go to here. That makes sense? Another way of indicating it, let's just take this point. Now, I'm going to draw a little arrow. Now you can see it. There's an arrow that indicates what your y coordinate is, right? If I double the length of that arrow, it's going to go down to about here. So here would be a point. I really ought to switch colors. If I double the length of this arrow, now I've offset it a little bit to the right, the actual point on the graph would be about here. There's a point on the log 2 graph. Here's a point on the log 2 graph. Let me go ahead and use blue to indicate these 2 points. You can do this either way. Okay, I could have drawn horizontal line here, horizontal line here. Is this one halfway between this line and the x-axis? Well, close enough. That makes sense? So that this value is twice as big as this value. Okay. Now we could do that for all of these points. And we could use either arrows or horizontal lines, but it gets kind of messy. By the time we get out here, we know that we're going to have to go twice this far from the x-axis from this point. So that's going to put it up here on the y equals 4 line. to avoid the score line over here, so it doesn't interfere. So one more at this point here has to go twice as far. So it has to come down to this line. And now I can sketch the curve that I've constructed. The graph has the same basic shape as the log graph, but every point is twice as far from the x-axis and on the same side. Does that make sense? That's how you do vertical stretch. Okay. Now, log of x minus 2. Okay, let's make it x plus 2. What about the graph of 2 log of x plus 2? How does that change compared to the graph of y equals 2 log x? Okay, this shifts place x by x minus h, where h equals -2. So that x minus -2 is x plus 2. Shift -2 units horizontally. So we can do that pretty easily. I'll use arrow. How long is an arrow? 2 units long. Here's 2 units, right? Arrow represents 2 units left. Now, this isn't a graph point. That would be like the origin moving 2 units left. But we use the same arrow to labels in the wrong place now. Okay, so this point's going to move over 2 units to the left. This point will move over 2 units to the left. Here's a point on the graph we know it'll move over 2 units to the left. This point will move over 2 units. This point will move over 2 units to the left. So I get points here, 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 and here. Probably should have made that one orange. Have another good color to use. So I'm just gonna kind of erase that. We know 2 units is this much, 2 units to the left is that much. Every point was 2 units to the left. And now we have this graph. Okay. And if we want to shift it vertically, well, we can move it up or down with a vertical arrow. All that makes sense? It should, because we talk about transformation since the first week. Okay, that takes a while for that to sink in. Everybody says it's tough to get students to understand transformations. Okay. It's one of the most important things you can understand for understanding the behavior of functions. And they make a lot of stuff in calculus a lot easier if you understand in terms of transformations. Unfortunately, most calculus courses, including mine, I suppose, you can't assume that people understand transformations, so you don't talk that much about it. you do these algebraic proofs, which are much harder to understand. Either that, or you don't do any proofs at all, which means you're not really doing the calculus. Okay? That's in defense of the way I do this. Okay? I mean, nobody's telling me to defend it, but you always want to justify what you're doing. Okay? Don't know if I'm right or wrong. No worse than what everybody else is doing. Okay? And I think it gives you some insights that you would not otherwise have. Especially if you're going to go into fairly rigorous calculus type courses. If not, you've learned a lot about how to maneuver on a coordinate set of coordinate axes, and you've learned a lot about how to use graphs. And that's all important. Yeah, we got to get some algebra going. Doing pretty much okay with that. Okay. So there we have it. Now, if I look at the homework that you have coming up, there are a couple of other transformations. I'll probably talk about them. What if we did y equals negative log of x? What would that do to the graph? Well, all your y values that are positive will become negative, and all the negatives will become positive. That would take this graph, or this yellow graph, and flip it around the x-axis, right? Okay. What if we replace x by negative x? Do the graph of log 2 of negative x. Well, that flips it around the y-axis. Okay. That actually probably turns out to be a fairly useless graph, but maybe not in some cases. Okay.